So in math, there's something called the transitive property of equality, of inequality, and there are other types of transitive properties, but basically they allow you to make a statement about how to compare two things once you know how each of those things compare to a third number or expression. So that applies to rates of growth as well. So this is asking us to show that this function, root 10x plus 1, and root x plus 1 grow at the same rate. And we can show that by showing that they both grow at the same rate as root of x, square root of x. So if we can show that they both grow at the same rate as square root of x, we can show that they both grow at the same rate as each other. I mean, we could just compare them together, but sometimes you get limits that are a little bit awkward to handle in terms of the algebra, and even L'Hopital's rule can turn into a mess. So if you can compare them to like a simpler version, like root x, it kind of makes the limits just easier to evaluate. But in essence, we're basically showing that if f grows at the same rate as g of x, and let's say g grows at the same rate then f grows at the same rate. F and h grow at the same rate. Alright, so that's what we're trying to show, or that's what we're using. Alright, so let's just quickly take a look at these limits. Let's compare root 10x plus 1 divided by root x. Notice it was actually it was a good idea to put the root 10x plus 1 on top, not because it would be wrong otherwise, but because we're going to be able to use this property of square roots, right? The square root of the numerator divided by the denominator is just the square root of the fraction in general. And then by situating it like this, the inside becomes easy to understand because it's just 10 plus 1 over x once you simplify. And as x goes to infinity, we can see this goes to 0, which means this whole thing goes to root 10. All right, and then now let's compare the other one, square root of x plus 1 divided by root x. Again, it was a good idea to put the root x plus 1 on top, because now I can count on the limit working out pretty nice. This is 1 plus 1 over x, so this goes to the square root of 1, which is 1. So don't be concerned that they didn't end up being the same thing. They're not the same thing, right? It's not that you get the same answer. It's just that this first ratio implies that root 10x plus 1 and root x grow at the same rate. And this bottom one, this result here, implies that root x plus 1 and root x grow at the same rate. So it's not that they get the same, we get the same answer in both limits, but whatever we get, if we get a non-zero, I mean, we get a number, then the two functions we're comparing grow at the same rate, a number that's not 0. And that happened in both cases. So then we can claim that root 10x plus 1 and root x plus 1 grow at the same rate. So we can order functions from slowest to fastest in terms of growth rate if we compare them. using the definition. So let's do this. I've got 4 functions here. To order them, I'm going to do a bunch of comparisons. So let's start with comparing e to the x. Let's start with the end of the list to 2 to the x. So let's see, you get the limit as x goes to infinity of e to the x divided by 2 to the x. Now before we use L'Hopital's rule, we can probably get around it. I can write this as e over 2 all to the x. Now e is bigger than 2, so this is a number bigger than 1 raised to the infinity, so this is infinity. So that means that e to the x grows faster than 2 to the x. Alright, so I guess apparently not all exponential functions are the same. So now let's compare e to the x to ln of x to the x. So we've got the limit as x goes to infinity of e to the x divided by ln of x to the x. And again, I can write this as the limit as x goes to infinity of e over ln of x to the x, which goes to, let's see, well, it goes to 0 to the infinity, right? This is a 0 to the infinity type of case. And so that's 0. I know 0 to the infinity sounds like an indeterminate form, but it's not. You're thinking of 1 to the infinity. Alright, so what does that mean? That means that e to the x grows more slowly than ln of x, right? We got 0, so that means the denominator is going faster than the numerator. So e to the x grows more slowly than ln of x to the x. Okay, so we're starting to get a picture here. Now let's compare e to the x to the x, and I would be willing to bet that since this looks almost like the other one, except that we have an x instead of ln of x, I'd be willing to bet that this grows, that x to the x grows much faster. So again, this goes to 0 because e over x as x goes to infinity approaches 0. So now this shows us that e to the x grows more slowly than x to the x. So at this point we actually are pretty much, we don't have to do many more comparisons. We've got 2 to the x has to be at the end of the list, right? Because e to the x grows faster than it, but e to the x grows more slowly than the other guys. So we're ordering from slowest to fastest. So I've got so far 2 to the x, and then I know e to the x is next. But now I got to compare x to the x and ln to the x. And that should be, you could probably predict that x to the x will probably go faster, but let's just confirm that. So we'll compare x to the x to ln of x to the x. So if you take the limit as x goes to infinity of x to the x, ln of x to the x, then we've got the limit as x goes to infinity of x over ln of x to the x. So this is where, we could, technically we've got an infinity to the infinity case. And actually that's not an indeterminate form. Infinity to the infinity is infinity, right? So the inside is going to go to infinity simply because x grows faster than ln of x. So you can do that off to the side if you don't believe me, but you'll get infinity, and that means that x to the x grows faster. Alright, so that puts our last two functions in order. Alright, so if someone was going to give you money that grew at a certain rate, the best rate would be x to the x, followed by ln of x to the x, followed by e to the x, followed by 2 to the x. You can talk about rates of growth for functions that are not defined as explicitly, but if you know if you have a graph of the ratio of those two functions, then you can determine which one grows faster. So this says that the graph of f divided by g is shown. So I might just indicate that more rigorously by saying the limit of x as x goes to infinity of f of x over g of x can be determined by the graph, and it looks like that's infinity. Sorry, that was a disgusting infinity. Right, that looks like that's going off to infinity, but that must mean, therefore, that f grows faster than g. Right, if this graph is going to 0, we know g would be growing faster than f. And if it was going to some non-zero number, we would know that they grow at the same rate.